Hey everyone, welcome to The Explainer. I'm so glad you're joining me for this one, because today we're looking at something absolutely fascinating: how to build a bulletproof safety system literally from the ground up. If you've ever found yourself wondering how these massive, high-pressure chemical facilities manage to run safely day in and day out without catastrophic issues, well, you're exactly in the right place. We're going to decode the ultimate blueprint for what industry insiders call mechanical integrity.
Let's just dive right in. Picture it. You've got a sprawling chemical plant. We're talking miles of complex piping, towering pressure vessels, and these giant storage tanks packed with hazardous, highly reactive or toxic materials, all under immense pressure. Obviously, the stakes here are astronomically high. So, the million-dollar question is, how do you prevent a facility like that from just breaking down? Because when you're dealing with environments like this, a simple equipment failure isn't just a headache. It carries terrifying potential consequences for the crew, the surrounding community, and the environment.
But there's a really critical shift in perspective we need to talk about right up front. Avoiding these kinds of disasters, it isn't just about begrudgingly ticking off regulatory compliance boxes. As the Center for Chemical Process Safety points out, quality mechanical integrity is consistent with good business practices. Seriously, when a company implements a top-tier safety system, it's actually a highly profitable strategy. It slashes unplanned downtime, stretches out the lifespan of incredibly expensive equipment, boosts product consistency, and ultimately saves a massive amount of money. Put simply, good safety is just good business.
So to really understand how this magic happens, we're going straight to the gold standard. Our primary source material for today's explainer is the definitive Guidelines for Mechanical Integrity Systems, published by the Center for Chemical Process Safety. Think of this as the master playbook. It's what the absolute best facilities around the world use to keep their gear safe, reliable, and functional. And today we're extracting those core methodologies right out of these pages.
To keep things organized, we're going to treat this explainer like a literal construction project, built out in 4 critical phases. We'll start with 1. Beyond breakdown maintenance, then move into 2. Leadership and responsibility, followed by 3. Defining the equipment scope, and finally wrap up with 4. The proactive ITPM plan.
All right, phase 1, beyond breakdown maintenance. Let's lay down the foundation.
At its core, mechanical integrity, or MI for short, is defined as the programmatic implementation of activities necessary to ensure equipment is suitable for its intended application throughout its life. It's a bit of a mouthful, right? But I really want to emphasize those 2 phrases, programmatic and throughout its life. Because this isn't just some one-and-done checklist when you first install the gear. No way. It's an ongoing, highly dynamic lifecycle commitment. It's a living, breathing system that tracks every single piece of equipment from the very second it's designed on paper to the day it's eventually decommissioned.
Now, it's absolutely crucial to contrast these 2 completely different philosophies. Back in the day, a lot of industries relied on breakdown maintenance. Run a machine until it literally breaks and then figure out how to fix it. It's completely reactive. But as we know, waiting for a pipe to burst is entirely unacceptable when you're dealing with hazardous chemicals. Proactive MI completely flips the script on this. It's predictive. The whole goal is ensuring ongoing durability and catching potential failures way before they ever get the chance to happen.
And that brings us to, honestly, my favorite piece of industry alphabet soup. You absolutely have to know this acronym, RAGAJEP. It stands for Recognized and Generally Accepted Good Engineering Practice. RAGAJEPs are basically the proven, consensus-based codes and standards published by the top technical experts out there. So you never have to guess how often to inspect a high-pressure boiler or exactly how to weld a highly specific type of pipe. You just start with your RAGAJEPs. They act as the proven, rock-solid starting point for literally any valid mechanical integrity program.
Moving right along to phase 2, leadership and responsibility. Let's talk about why taking ownership matters. Now we're shifting over to the human element, because let's be real. The most meticulously planned safety system is utterly useless without the right architects leading the charge and taking absolute ownership. One of the core leadership concepts here is what's called the operating window. This refers to the safe upper and lower limits of process conditions, things like temperature, flow, and pressure. But notice this key detail. This window is defined by the current and projected condition of the equipment itself. So, technical leadership has to rigorously define this strict operating window. They are the ones who must set the hard rule that the facility's business goals will only ever be met while staying inside those safe, physical limits of the hardware. No exceptions.
And to maintain those strict limits, leadership relies on tools like a roles and responsibilities matrix. This is brilliant because it seamlessly delegates tasks across maintenance, engineering, and operations. For every specific activity, someone gets assigned an R because they are responsible, an A for who approves it,
an S for who supports the task, and an I for who simply needs to be informed. It completely eliminates the "I thought you were doing it" confusion. Everyone in the plant knows exactly who is accountable for every single safety activity.
Okay, Phase 3, defining the equipment scope. Let's establish our boundaries. So how does a facility actually decide what needs protecting and monitoring under their ML program? Well, the most obvious candidates are the core containment items. We're talking about pressure vessels, atmospheric storage tanks, massive sprawling networks of process piping, and the pressure relief devices that act as your critical safety valves. Naturally, if these things hold hazardous chemicals, they absolutely have to be rigorously managed. But it's not just about jotting down a quick list. The scope has to be heavily documented. You have to be able to answer, why is this specific pipe included while that one over there is excluded? Establishing really clear, thoroughly documented selection criteria is vital to making the whole program work.
But we definitely can't stop at just the obvious stuff. We have to rope in critical additions that often fly under the radar. Think about the systems that actively mitigate disasters, like emergency shutdown systems, nitrogen purge utilities, and specialized building ventilation that handles toxic vapors. Believe it or not, even temporary transfer hoses and vendor-supplied equipment that just connects to the plant temporarily have to be pulled into this scope. The rule of thumb is simple. If its failure could lead to a catastrophe, it belongs in the mechanical integrity program. Period.
And that brings us to our final phase, number 4, the proactive ITPM plan, time for execution.
This right here is a very heartbeat of the entire program. It's where all that prep work we just discussed finally translates into actual boots-on-the-ground action. ITPM stands for Inspection, Testing, and Preventative Maintenance. Definitely lock that acronym into your brain because this is where theoretical, on-paper safety becomes a daily, ground-level routine. It's the scheduled, recurring list of tasks specifically designed to hunt down equipment degradation way before it ever gets the chance to evolve into a full-blown incident.
So let's see how this actually builds into a structured process. Our source material outlines a really elegant 5-step method for creating an ITPM plan. Step 1, you organize the equipment into logical classes, like, say, grouping all your centrifugal pumps together, just to make the sheer workload more manageable. Step 2, gather all the engineering data and history. Step 3, assemble a solid, multidisciplinary team of experts. Step 4, actually select the specific tasks and intervals. And Step 5, maybe the most important one, document the technical basis for every single decision you just made.
Now, when that expert team starts selecting tasks, they're essentially choosing between 3 primary weapons. First, you have inspection, which is all about detecting the onset of a physical failure. Think of using ultrasonic waves to measure a vessel wall to see if it's corroding and getting too thin. Then there's testing. This assesses conditions or hunts for hidden failures, like intentionally triggering an emergency shutdown valve just to make 100% sure it actually closes when you need it to. And finally, preventive maintenance, which aims to stop premature failure entirely. This can be something as simple but absolutely vital as routinely lubricating a massive pump.
But you might be wondering, how often are you supposed to actually do these tasks? Well, that's where interval factors come into play. The team doesn't just guess or pull a number out of a hat. They look closely at the equipment's age, the specific corrosiveness of the materials it handles, known damage mechanisms like stress cracking, and the actual historical operating data of the plant itself. And remember those RAGAJEPs we talked about? They rely heavily on those, adjusting the frequency of these tasks based on how fast the equipment is, theoretically and historically, deteriorating in the real world.
Finally, we've got to recognize that this blueprint, it's never truly finished. The final critical piece of the puzzle is continuous auditing. You have to constantly track your metrics. Are we actually adhering to our inspection schedules? What are the long-term trends in equipment condition telling us? Are we catching the near misses? By continually auditing all this data, management ensures they're optimizing their resources and that the safety program is actually adapting to the real-world wear and tear of the facility.
Which leaves us with a final, slightly provocative thought to wrap up today's explainer. I want you to take a hard look at your own environment. Whether you work in a giant industrial plant, a corporate office, or really any complex system, are the safety and operational systems you rely on every day just sitting there, waiting to break down? Or are they proactively managed with a continuous, structured integrity program? Because true safety isn't just the absence of accidents, it's the active presence of a well-executed blueprint. Thanks so much for learning with me today, and I'll catch you in the next explainer.